In this video, we're going to be starting the chapter of thermodynamics and equilibrium. So thermodynamics we studied in first semester is to study the relationship between heat and other forms of energy, especially involved in chemical and physical processes. So it's in conjunction with physics, and we actually have an area of chemistry called physical chemistry that studies these things. So what we're going to introduce this time is something called internal energy, which we symbolize by the letter U, and it's simply the sum of the kinetic and potential energies of the particles. And so you think, okay, here's a glass of water sitting on a desktop. Does a glass of water have any energy to it? Well, yes, that's the internal energy. So all the water molecules, because this is a liquid, have some kinetic energy. They're all moving around. Not to mention the fact that there's attractive and repulsive forces going on, which is the potential energy. So that is an example of the internal energy there. This is a review from that chapter in 1211, that a system is simply the substance or mixture under study. And so here is a closed-in system. So the system is in pink here. And everything that's outside of this box is the surroundings, including the air. Okay. Another term that we learned in chapter 6 was a state function. It's a property that depends only on its present state, not as how it gets there or by variables of temperature and pressure. And so the example here is I can take path X up Mount Kilimanjaro, which is much more difficult, is rock climbing and that type of thing, or path Y, which is what they call a switchback system. But basically, the state function says is that the height that I start at and the height that I end at is the same. And so that's what a state function, it doesn't matter if I take path X or if I take path Y, it's the same, the thermodynamics is the same either way, okay? And so we're going to be looking at the change of internal energy, which is measuring the exchanges of energy. And the two that we're going to do it is heat, which is what we studied in chapter 6, which is the energy that moves in and out, which is symbolized by Q, and work, which is what happens as a result when a force moves an object through a distance. So work is equal to force times distance. For heat, if it's endothermic, it's positive, which means the heat's flowing from the surroundings into the system. A negative work means a negative energy, heat. A negative heat. So a positive is called endothermic. Heat flows from the surroundings to the system. A negative is exothermic. Heat flows from the system to the surroundings. Okay. Whereas for work, okay, positive sign of work means that the work is done on the system. So we're going to look at a plunger system. And so when you push in the plunger, the work is being done on the system. A negative sign means the work is being done by the system, so a plunger or a piston. So that would mean the piston raising up. And so here, the system is doing the work because of the fact that it's going up, so it's going to be negative, and the heat is going to be positive because the heat's coming from the surroundings into the system. So here, work is negative. Make sure that's right. Yes. So this is a negative sign, and this is going to be a positive sign because the heat's flowing from the system, or from the surroundings into the system. So the first law of thermodynamics says that basically the way that we normally put it is the fact that energy can be neither created nor destroyed but transferred. So basically the change of the internal energy is the change, it's the heat plus the work. So if you think about this, when I intake food, Of course, we maintain a body heat, so that's the heat coming out. That's the small q of heat coming out. And then I also am able to move my body, so that's the work. So that would be the food intakes to do that, okay? Or another example is the sun shining energy into the flower. And of course, all plant life undergoes photosynthesis. And so then it basically gives me heat going in, or I'm sorry, out as a process of that photosynthesis. So how does work deal with chemistry? What we're going to be looking at is basically something like the internal combustion engine or your car engine. If the container has a movable side, which your car engine does, that's called the pistons, then work would be done to move that aside. And so the work then is the negative pressure times the change in volume. And work is a unit of energy, so it's in the units of joules. And the change in volume is found where the change in volume is calculated for the change in moles. We're not going to actually do any calculations here. But here's like the piston in your car. Okay, so I have gasoline inside the car, and I have a cylinder with the piston there. And so I have a volume 1. Okay, I heat this up by putting heat into the system for an internal combustion engine. Of course, that's done by the burning of the gas. Okay, and the volume goes up, and therefore the work, the change in height is going to be related to the change in volume here, and the piston goes up, and so the work has been done by the system to do this. Okay, and so in this type of system, your pressure is usually constant, say 1 atmosphere, and basically what changes is the change in volume there. Other things from chapter 6 we want to review is the fact that the delta H stands for enthalpy. So and that the enthalpy is equal to the heat at constant pressure. Okay. The other thing we learned is that you can find the change in heat for a standard system by taking the sum of the delta H's of formation of the products minus the sum of the delta H of the reactants. And these two things here are the coefficients. So it looks like a complicated equation, but it's really not. So looking at this example here, okay, the delta H naught, it's the products first, okay. I'll tell you what, I'll do this by color coding it. Okay, so the products first is going to be the sum of the products. So I have 2 times the delta H of formation for water as a liquid, plus 2 times the delta H of formation for SO2 as a gas, minus the reactants then. It's going to be 2 times the delta H of formation for H2S, plus 3 times the delta H of formation of O2. So basically, this coefficient here goes to, well, this is the wrong one, but here and here and here and here. So I just basically list all my products first, times the coefficients in front of the chemical equation, minus the chemicals in the back. Okay? So then my delta H naught is going to be 2 times the water as a liquid is a negative 285.8, plus 2 times the SO2 as a gas, be this one, minus 296.1, minus 2 times that of H2S as a gas, which is this one, plus 3 times oxygen, which is not listed here, but oxygen is 0, Okay, and so the first parentheses, set of parentheses, is a negative 1459.9 minus 2 times the negative 20.1 is a negative 40.2. And so when I add those two together, I get a negative 14,419.7 kilojoules is the unit. It's exothermic, and it's exothermic because of the negative sign there. Okay, and that will be the end of this video.